Meet Maya. She's in 6th grade, and today she has a math project. She has to flip a coin 20 times and record the results. She figures, easy, it should land heads exactly 10 times and tails exactly 10 times, right? But when she finishes, she gets 13 heads and only 7 tails. Now she's worried she did something wrong. She didn't, and by the end of this video, you'll know exactly why, and you'll be a probability pro. Before we solve Maya's mystery, let's make sure we understand what probability actually means. Probability is just the chance that something will happen. We write it as a fraction, favorable outcomes over total outcomes. The answer is always between 0 and 1. 0 means it will never happen, like rolling a 7 on a regular die. 1 means it's guaranteed, like the sun rising tomorrow. Most things we deal with fall somewhere in between. Pretty simple so far, right? Good, because here's where it gets really interesting. Now, theoretical probability is what math predicts should happen in a perfect ideal world. When Maya flips a coin, there are 2 equally likely outcomes, heads or tails. So the theoretical probability of getting heads is 1 out of 2, which equals 50%. This is the answer you get by thinking it through with math. No experiment required. It's like a prediction. You're saying, if everything is perfectly fair and random, here's what I expect. Maya expected exactly 10 heads out of 20 flips. That makes sense, but reality had other plans. Experimental probability is what actually happens when you run a real experiment. Instead of predicting, you do it. Flip the coin, roll the die, spin the spinner, and record your results. The formula looks the same, but uses real data. Number of times the event happened, divided by total number of trials. Maya flipped her coin 20 times and got heads 13 times. So her experimental probability of heads is 13 out of 20, which is 65%. That's different from 50%. And here's the secret. That's completely normal. Let's find out why. So why don't experimental and theoretical probability match up perfectly? Think of it this way. Theoretical probability lives in a perfect math world where everything is exactly equal. But in real life, randomness is, well, random. When you only flip a coin 20 times, you might get a streak of heads just by chance. It doesn't mean the coin is broken or that you did anything wrong. Here's the really cool part. The more trials you run, the closer your experimental probability gets to the theoretical probability. This is called the law of large numbers, and it's one of math's most beautiful ideas. Let's put these 2 ideas side by side. Theoretical probability says heads should come up with probability 1/2. Maya's experimental probability came out to 13/20. Are both valid? Absolutely yes. Theoretical tells us the mathematical expectation. Experimental tells us what actually happened in practice. Neither one is wrong. Scientists, doctors, and engineers use both kinds of probability all the time. Theoretical helps them plan. Experimental helps them test. Maya is now starting to see her 13 out of 20 result isn't a mistake. It's just real-world randomness doing its thing. Let's try an example together, the kind Maya is working through right now. We have a standard 6-sided die. What's the theoretical probability of rolling a 3? There are 6 equally likely outcomes. 1, 2, 3, 4, 5, 6. Only one of those is a 3. So the theoretical probability is 1 out of 6, which is about 16.7%. Now imagine Maya rolls the die 30 times and gets a 3 exactly 7 times. Her experimental probability is 7 out of 30, which equals about 23.3%. Different from 16.7%, but with only 30 rolls, that's totally expected. Here's another example. Maya has a spinner divided into 5 equal sections. 2 are red, 1 is blue, 1 is green, and 1 is yellow. What's the theoretical probability of landing on red? There are 2 red sections out of 5 total, so the theoretical probability is 2 over 5, which equals 40%. Now Maya spins it 50 times and lands on red 17 times. Her experimental probability is 17 out of 50, which equals 34%. Again, different from 40%, but pretty close. And with more spins, they'd get even closer. Maya's getting the hang of this.
One more example, this time with cards. Maya writes the letters M-A-T-H-R-O-C-K on 8 cards and puts them in a bag. What's the theoretical probability of picking a vowel? The vowels are A, O, and, well, that's it, A and O. Wait, let me count. A and O are vowels. That's 2 vowels out of 8 cards. So P of vowel equals 2 over 8, which simplifies to 1 over 4, or 25%. Maya draws a card 40 times, replacing it each time, and gets a vowel 12 times. Experimental probability? 12 out of 40, which simplifies to 3 out of 10, or 30%. Nice and close to 25%. Here's the most important idea in all of probability, and it's one Maya is discovering right now. Let's say we flip a coin over and over. After just 10 flips, we might get heads 7 times. That's 70%. Pretty far from 50%. After 100 flips, we get heads 53 times. That's 53%, much closer. After 1,000 flips, we get heads 498 times. That's 49.8%, incredibly close to the theoretical 50%. The more trials you run, the closer experimental probability gets to theoretical probability. This is the law of large numbers, and it's why scientists run huge experiments instead of small ones. All right, your turn. Let's solve one together. A bag contains 10 marbles. 4 are blue, 3 are red, and 3 are green. First question, what is the theoretical probability of picking a blue marble? There are 4 blue marbles out of 10 total, so P of blue equals 4 over 10, which simplifies to 2 over 5, or 40%. Now, Maya reaches into the bag 20 times, replacing each marble, and picks blue 6 times. What's the experimental probability? That's 6 out of 20, which equals 3 out of 10, or 30%. Theoretical says 40%. Experimental gives us 30%. Close, and both totally valid. Here's something really cool. Probability isn't just a school topic. It's everywhere in real life. Weather forecasters use theoretical models to predict rain, then update with experimental data from actual weather. Doctors run clinical trials, that's experimental probability, to see if a medicine really works. Video game designers use probability to make games feel fair and fun. Insurance companies use probability to figure out how much to charge you. Even the NFL uses probability to analyze plays. Maya's coin flipping project? That's real science happening at her kitchen table. Pretty awesome, right? Remember when Maya was panicking because her coin landed heads 13 times out of 20? Now she knows the truth. That's experimental probability doing its thing. It doesn't have to match the theoretical probability of 50% exactly. The two formulas are simple. Theoretical uses favorable outcomes over total outcomes. Experimental uses times it happened over total trials. The more trials Maya runs, the closer her results will get to the theoretical value. From confused to confident. That's Maya's probability journey. And now it's your journey too. You've totally got this. Go